be the chair for this session about industrial security, and I will add IoT security because as you're gonna see, we're gonna talk about IoT a lot. Before actually starting, I'm asking Francesco if he can enable the microphone to just test a little bit the audio, and then we can start with the first speaker, Professor Merro from University of Verona. So welcome, Professor Merro. The floor is yours.
Thank you. Can you see it? The presentation? Mario?
It's working.
Okay. So this is my name is Massimo Merro. I'm professor of computer science in Verona. This is a joint work with Ruggero, Lanotte, Andrei, Munteanu. Actually, what I'm going to present here is a paper that already appeared in the Computer Security Foundation Symposium of the last year. And actually, there is something new that I will tell you. Well, just to go straight to the point, on industrial control system, there's a bunch of new vulnerabilities, this kind of cyber physical attacks. Well, basically, eventually, the goal of those attacks is to reach the OT technology of cyber physical system, industrial control system. So at the end, the goal here is to take control of the controllers of PLC in order to govern some physical process and eventually to create some physical damage. So this is a kind of attacks which are quite different from IT attacks, from Facebook breach we just heard. The point here is to create physical damage, not necessarily catastrophic damage, but to take control possibly of the physical process for some reason. So just a few words about what is a PLC. A PLC, quite simple piece of logic. That is doing an iterative behavior that's called a scan cycle. Basically, you read the measurement of the physical process, then the logic decides to do something, and this operation, those commands are sent to the actuators that take care of this physical process. You open some pump, you switch on some pump, you open some valve and things like that in order to take care of the physical process and to keep this physical process in some equilibrium. And of course, this kind of controllers can be compromised, and that's really the point. The final goal is to compromise this controller, and not only to create a disaster. This kind in this picture you have centrifuge because the most famous attack was Stuxnet. The goal was to destroy centrifuge in Iran, but it's not only that the point, but the point is that once you have a control of PLC, you can propagate to the rest of the system. You can completely provide fake information to the SCADA system that is supervising what is happening. So basically, the situation is like that. You have a network of controllers that are connected on something that is called the field communication networks. And you have PLC. They may be, most of the time they have for sure USB ports for technicians, and very often they also have an internet port. If you go to show them, it's easy to find many PLC that are already in the internet. And the point is that if one of this PLC gets compromised, there is an injection of some malware. This malware can easily propagate to the system and can take control of the physical process. So what is the proposal in this paper? Well, the proposal is to use some formal technique. It's called a runtime enforcement. As the word says, the idea is that at runtime you want to enforce good behaviors, actually safe behaviors. How do you express the safe behavior? With safe properties. Something like, if you have a water tank system and you don't want to run your tank in an empty state. So, a property is saying something like, if the level of water in your tank is low, the valve should be closed. This is a kind of safety property and similar things. So the idea is that to enrich the system with enforcement, with introducing some safe and secure proxy, that does enforcement of some properties. So the enforcement is not about all the complete behavior of the PLC. You're not talking about performance, but just about safety, ensuring certain properties. And you want to be sure also that you're not doing only enforcing, but in the while you are doing enforcing, you're not doing bad things. Let me clear what we mean with that. So basically, we start from a formal language to express a network of compromised controllers, and then we express safety properties using, well, well-known regular properties. And why regular properties? They are quite expressive, and they fit quite well in this iterative behavior of PLC. They have this scan cycle, and that's quite good for regular properties. From these properties, when you want to enforce one of these safety properties, we synthesize enforcer as kind of automata, edit automata, like correcting automata. They are just there to correct actions. And what are the properties that we want to have in this enforcement at runtime of the behavior of the PLC? Well, of course, we want to be transparent. We don't want to change the semantic of the controller. We want soundness. If the enforcer is enforcing a certain property, you are sure that all the execution trace of that controller respect that properties. We don't want to introduce deadlock, for instance. With enforcement, the enforcer should not block, should not deadlock the PLC, and of course, we should not introduce the vigilance. And something quite interesting, what we want also that the enforcer should be able to do some mitigation. Mitigation means, if the controller is not able to complete correctly the scan cycle, well, the enforcer should go on and take the control, like a safety controller, and to complete the scan cycle in a safe manner, not in an optimal manner. You can know about that, but at least in a safe manner. And of course, what you want is that all those properties, they scale on a network of controllers. Well, that's what you have. Now, this slide, don't just get worried about it. But just I want to show you that with regular properties, you can express a quite wide class of interesting properties about PLCs. And so we end up with a family of and subfamilies of properties that we are able to enforce. So the results are, let's keep transparency is quite, let's see what soundness means. Well, soundness means that you don't have unsafe executions of your system. What it means unsafe? Well, it means that they don't respect some safety properties enforced by the enforcer. So basically, if your controller is going to do a trace which is not safe, is not respecting the safety properties of your enforcer, while the enforcer take care of correcting the execution of that trace. So of providing a safe execution of the controller, safe, not optimal, in order to ensure soundness. And of course, what is interesting about deadlock, this may happen. That's quite interesting is that the malware may be interested in driving the PLC for a while and then stopping at some point in order to deadlock the system. Well, if this happens, the enforcer must take into action and must complete the scan cycle in a safe manner in order to avoid deadlock, and the PLC will continue working if it's able to do so. But at least if it's not able to do so, the enforcer is able to keep going in a safe manner, saving time for engineers to see what happens in this PLC. And similar things for divergence freedom. You don't want that your system goes into divergence, and you want to avoid this. So you want to avoid that because if this happens, the PLC basically blocks because there is some timeout, some hardware timeout in PLC, and it's not going to continue its execution. So what we did at the end is not just a theoretical work. Then we tried to do, we did an implementation. Let me say what we did. So we consider a water filtration system, and we did an implementation. The physical part is simulated in Simulink. We don't have the water tank system, but the PLC, actually we have, we implemented it with OpenPLC, which is a quite very effective way of implementing PLCs. Effective in terms of performance, very, very similar to real PLC. We did this on Raspberry Pis, and then we implemented the enforcers in FPGA, because of course, we need some enforcer. The enforcer must be performant with respect to the PLC, because they must enforce in time in order to, before the end of the scan cycle. What we did in our test, then we injected the malware directly in the code of the PLC, in the ladder logic. This PLC, they are running sample code that's called ladder logic. And basically, when the attacker takes control of the PLC, does an injection of code. So we did different kind of injections, and we tested the effectiveness of our enforcement in order to ensure safe behavior of the enforced system. Actually, in this case, we have 3 tanks, 3 PLC. They are connected in network, then they are exchanging some information about some balance of water. So summarizing, what we started from a formal representation of enforcement based on runtime enforcement, and we formally proved a number of properties of the enforcement mechanism derived from our synthesis. So we have a class of properties, a language of properties, and when we enforce those properties with enforcer, we have those properties proved formally. Well, as I told you, this is quite short time to tell you the story in detail, but you can find more detail in the CSF paper of the last year. Actually, we are finishing in a few weeks the full papers, and these are the references shown here. There are other references, on similar topics we are working with. I hope I'm in my 12 minutes. Thank you.
Yes, perfectly in time. Thank you. So we actually have one question. It was actually talking about the slide number 7. They want some recap on the content of slide number 7. If you can give a few words on that, extra words.
Here we are.
Yeah, they just asked for some recap.
Can you tell me? Can you read me the question?
So the question is just asking for a recap for the content of the 7th slide.
Oh, okay. Okay. A recap is, well, we have a language to express networks of possibly compromised controllers. Okay, a formal language with a formal semantics. We have a language to express properties that we want to enforce on PLC, not only on one, on a network of PLC. And these properties are basically expressed in some kind of regular language, just because, this PLC, they have an iterative behavior. And from these properties, we synthesize enforcer that we attach to the PLC as a secure proxy in order to ensure that this safety property is preserved at runtime, is enforced at runtime. And then we prove that there's a enriched system, you have the original networks and is enforced by a bunch of enforcer as a number of properties. So the resulting enforcement as a number of properties, the semantic is preserved, the properties are really enforced, and you're not introducing bad things like deadlock or divergency. That's more or less a recap.
Thank you. I think was great. So for if we have other question, please do use the question and answer feature outside of WebEx if you need to ask other question. I'm not seeing other question coming, so I will thank the Professor Merro and moving to the next speaker.
Thank you.
Thank you for joining us. So while we are switching, next speaker is Francesco Palmarini from University of Venezia. Not sure if he's still working there. And Francesco is gonna tell us about what he's doing right now. Francesco, can you hear us?
Yeah, I can hear you.
Yes,
can you hear me?
Great. Yeah, let's see also if we can get your slide online.
Okay.
Okay, I see your slide.
I guess you cannot see me because I'm from Android, so.
Yeah, so we have slides separate from Francesco, so it's gonna be, so sorry for that, but that's some technical issue that we had, okay? So thank you, Francesco, the floor is yours.
Okay, thank you, Maria, for your kind introduction. So next slide, please. Okay, so in this presentation, we are talking about embedded devices in general, because yes, IoT devices are, first of all, embedded devices typically, right? And at the heart of this type of devices, there is typically one component, which is the microcontroller. This component basically integrates CPU, RAM, storage, and other peripherals in a single monolithic package. Sometimes there is also some external memory because you might want to store additional resources, code, or whatever that doesn't fit into the internal memory, okay? And typically these components, well, you can find everywhere because, I mean, embedded devices, still you can find them everywhere, okay? They are typically low cost, low resources, low power, and so on, okay? So next slide, please. So in this scenario, you typically can do any kind of software exploits, software-based attacks that we are already familiar with. They are extremely dangerous, important to study, of course. The motivation can be from reverse engineering, and it is also what we do. So we are kind of attackers in this context. You might want to steal some confidential information that are stored into the devices, so password keys, communication protocols or whatever. And sometimes you might also want to break the intellectual property contained into the memory of the device itself, because you might want to clone the device. You may want to make a counterfeit version of the device. So this is a problem not only a security problem, but also a kind of industrial problem, because you are actually losing money because of this. So this is very important. Next slide, please. Okay, so yes, software attacks, as I said, are extremely important, dangerous. We all know that, but as so are the hardware attacks, because we are talking about physical devices, not just software in a computer. Okay, this is a piece of hardware. And hardware attacks are also important because nowadays you don't need fancy, super high-tech and cost equipment to make this kind of attacks. You can do it using very cheap hardware, typically, not always, but typically. So hardware attacks can be divided in active and passive attacks. On the active side, you have all these fault injection techniques. Fault injection means that you want to cause some kind of errors during the computation, okay, of the firmware, basically. You inject something to cause this error, and this something is typically a clock glitch, some interference in the voltage supply line, EM or RF interference, lasers, and whatever you can get up to. The goal is to basically alter the intended execution flow, even if there are no actual bugs. Okay, for example, there is no bugs in a security check, and you want still to bypass this, then you can use this kind of hardware attacks to kind of create your own bugs. You do skip instruction, you influence branch decision, and so on and so forth. Okay, next slide. And then there are passive attacks. Passive attacks are basically side channel analysis kind of attacks. You might be familiar with Spectre, Meltdown, SGX enclave based attacks on the PC side. Here it is kind of similar. We want to collect and process any data information that we can get on the environment of the device while it is executing, of course. Okay. And this information, this data can be, the power consumption, some emission of the device, the execution timing, the dissipation, and so on. Okay, and typically you want to, leak something from the device, and often is, crypto materials, crypto keys, and so on. Next slide. Okay, so we are effectively talking about physically now attacking a device, and yes, there exists some level of protection that the chip manufacturer gives you. Typically you have some kind of readout prevention and protection mechanism, so you cannot read back what you have just written into the device once you have locked, okay, and protected it. You have some level of countermeasures against, for example, some kind of fault injection attacks, but the problem is that we are talking about cheap components, typically, okay, low-cost components, and this balance between security and cost is typically more towards the cost rather than security. So often this kind of protection mechanism is insufficient, and sometimes might even gives you a false sense of security while you are designing your own device, because you might say, okay, I'm safe because I've enabled all the protection mechanism, and still this is not the case because there are some other attacks that you can implement. Next slide. Okay, so the point is, okay, you have enabled all the security feature, you have done everything right, okay, even best practice, security best practices. So to give you an overview about the techniques, the methodology, the steps that an attacker does to basically attack this kind of devices, in this paper we try to analyze a real life case study that we made in collaboration with a company which is a spin-off of Focardi, which is ITASEC. This project is still under active NDA, so we cannot give you exactly every detail about the device, the attack, and so on. But still, it's very informative. So the device under test is a real device again, with the two main components on the PCB, which are two microcontrollers. We call the one red one and the other the blue one. They are connected through a shared bus, and on this bus there is also an external flash memory. The first problem is that we knew nothing about this component. We didn't even know that they were microcontrollers at the beginning, because the manufacturer has etched away the labels or swapped away the labels of the components. So we knew nothing basically about these components. So the first step was to do some reverse engineering of the PCB layout and the pinout of each component, and to look for matches online on all the datasheet that we can get online. Okay, and in the end we were able to identify correctly this component. Well, the flash memory is basically just nothing fancy, just a serial flash memory. The red microcontroller is a microcontroller with a one-time programmable memory, and two execution states, one development and one basically production, that disable every debugging feature that even in hardware, okay, totally disable every debugging feature in hardware. And this is also an AES hardware accelerator built in. On the other side, the blue one does contain a standard flash integrated memory with the firmware, of course, and serial bootloader that can be used in development to program, erase, verify, do whatever you want with a flash memory, and then you lock the device, you enable the protection, and you cannot no longer access and download the firmware. Next slide. Yes, just okay. The point is was that we downloaded the external flash memory, of course, because we can have access directly to it, and we found that it was probably encrypted with AES. So again, as you can see, they enabled everything they could from a security standpoint. They used the best practice, good cipher, and everything else. Still, we managed to attack these devices. Next slide, thank you. So the first one to attack was the blue. We used fault injection. The goal was to again extract the internal firmware from the internal flash memory. Okay. We used in particular a technique called voltage glitching, which amounts to injecting some disturbances, some glitches, some spikes in the voltage supply line in order to cause errors during the program execution. In particular, in this case, the integrated serial bootloader, which is a piece of software, and in particular, the security checks involved, okay, in telling the device if it was in production, and then all the security protection are enabled or in development mode. And in this case, we used the setup and the technique called arbitrary glitch waveforms that we presented at CAS in 2019. Next. So this this technique is very powerful, just 2 words, because it allows you to control any aspect of the attack in software using a computer. And with a relative cheap hardware, about 200 euros or even less, okay, you can build it by yourself, so it's very powerful. And for the first time, you can also control the actual shape of the glitch that you are injecting, okay? And this is important because it can optimize and gives you better performance, better attack performance, okay? And yes, there is also some genetic algorithm inside that allows you to kind of automatically find and optimize and tune all these parameters in software. So next. So with this, next slide. Okay, thank you. With this technique, we were able to successfully download the firmware by attacking the internal bootloader. We did a brief reverse engineering just to see if there was any use of that external memory, and it wasn't the case. So we thought, okay, it might be used the external memory just from the red device, not the blue one. So we started to attack the device again using fault injection, but this time we didn't succeed. So we switched to a more complex attack, a 2-step attack, in which the first step of the attack use side channel analysis, and in particular a technique called correlation power analysis, to do what? To recover the AES key that was used to encrypt or decrypt, in this case, the external flash memory on loading. So during the runtime of the microcontroller. Next. So CPA, just 2 words, is a very, very powerful technique that allows you, by measuring the subtle differences in the power consumption of the device, of the microcontroller, okay, and acquiring multiple power traces, okay. And every time you acquire a new power trace, even 1,000, 100, it depends on what you are doing, okay. Every time you acquire a new power trace, you change either the plaintext or the ciphertext. In this case, the ciphertext, because we are decrypting, okay. And you do some statistical analysis. In this case, we use a model called the Hemingway, okay, to model the power consumption, how the power consumption vary with varying the input text, so the ciphertext in this case. And we also split the full key, the full AES key, in multiple subkeys to reduce the search space. And then you apply the so-called Pearson correlation coefficient that gives you just a value between -1 and 1, with 1 is the best, okay, in this case. And you can evaluate for each subkey and each power trace whether your guess for that specific subbyte is correct or not. As you can see on the right, the blue trace here contains the correct guess for that subbyte because it has the highest correlation value, above even 0.4 in one case. Okay, next, thank you. So summing up, we were able to extract the IS key from the device just by putting a small shunt resistor in series to the power line of the device. So to measure the voltage differential with a differential probe, and so calculating the actual power consumption of the device. We use a USB scope connected to a computer to acquire all this data and performing the CPA attack and recovering the key. The next step was, okay, we can now decrypt the flash memory, the external flash memory, with a brief reverse engineering to understand what was in there and, the memory layout and stuff like that. And we said, okay, now we can craft our own payload, inject our own payload, and do some code execution attack, basically, okay? And this is what we did. So we put a very small payload that was reading the firmware, the internal firmware byte per byte, and transmitted it over a simple serial line to GPIO serial line, okay, connected to a logic analyzer or whatever you want, and you have your own firmware. Now we had just to trigger the loading. It was done just with a button on the board that was loading the procedure, basically, that was starting all this procedure that was loading the data, and you are done. So as you can see, even if you have a device and you are using all the standard protection mechanism available, you are still vulnerable to this kind of setup. Even if you are doing code review, even if your firmware is safe, you must still be aware of this kind of attack if you are designing an embedded device. So I think this is a good advice for embedded designers. Okay. Next slide is just a thank you. Okay.
Okay. Thank you. Thank you, Francesco. So do we have any question from the audience? Otherwise, I have tons of questions for you, but I'll keep it short. So one curiosity was when you were mentioning the device, when you were attacking the blue chip, let's call it the blue chip.
Yeah.
It was like a device specifically built to do glitching attack, or is a chip device that you use for this attack?
No, well, it is a whole setup that we proposed, as I said in that paper at CASA. It is
okay.
It is quite it's really simple. It's made of off-the-shelf devices and just some custom parts, but nothing fancy. Something that you can build even by your own. Okay, once you know the architecture and how does it work, it is just to build it, to make it work, but nothing fancy. Just I don't know, 150 or 200 euros of components. Really cheap. And probably in this case, you might even do it with even cheaper setup or even a simpler technique. I mean, I don't know. We used our technique, of course, because we are familiar, but still, it is very doable for, everyone. I guess that it is comparable in complexity with the software exploitation that we all know nowadays. I mean, I don't know if this is more complex or not than a heap overflow or whatever, as you imagine.
I think it depends on the knowledge of the people that is using. Okay. Thank you, Francesco, for the kind reply. I will move on the next speaker.
Thank you.
Okay. So our next speaker is Professor Romano from University of Napoli Federico II, and he's going to talk about the frameworks used for improving security in OT systems. So thank you, Professor Romano, for joining us. The floor is yours.
Thank you, Mario, for your introduction, and thanks everybody for being here at this session. It's a pleasure for me to present this work. The work is about our cybersecurity framework comparison tool. This is a joint work with Joe Mùrino, who is indeed the lead project investigator behind the things that I'm going to present today. Then we have Marina Ribaudo and my colleague Armando. I'm going to present the work today, and in order for you to have easier access to my presentation, I also provide here a QR code you might be willing to scan. So I will leave just a few seconds for you to grab your smartphones in case you want to have access to the presentation even offline for browsing through it after the panel is over. So if you are done, I will quickly move to the introduction. Basically, we had in mind to provide a sort of, let's say, orchestration tool that might be leveraged by people who are interested in somehow governing the chaos of information that currently characterizes the cybersecurity arena. So basically, we took a look at all of the information sources that are currently available in this field, and we tried to put some order inside such a universe. We took as reference points the main regulatory documents that are currently available, and I will expand just a bit on these in my presentation. Obviously, we also had other goals, and among such goals, we wanted to highlight somehow the differences that do exist between information technology scenarios and operational technology scenarios. And also on this, I will dedicate a specific slide because I think this deserves some mention. We also wanted to provide means for having a sort of comparative analysis of the cyber resilience level of network infrastructures and critical infrastructures in particular. And last but not least, we are educators, and so we were also interested in somehow fostering evangelization. So we are currently already leveraging such a tool in order to improve the way we teach about cybersecurity, which is one of my personal goals, for example. So I will, let's say, skip some of the details here, but just wanted to provide you with some context information about the main reference documents that we have at hand when it comes to assessing the level of resilience of an infrastructure. So basically you have the Presidential Policy Directive 21, which dates back to 2013. Then you have a fundamental milestone that is the Cybersecurity Enhancement Act from 2014. This is an important one because it somehow updates the role of the NIST Institute by assigning to them a different, let's say, role to be played when it comes to assessing the level of risk of an infrastructure. And obviously, we could not skip the National Cybersecurity Framework, which, by the way, is a sort of overarching work that tries to put together all of the references that I was mentioning. And indeed, I'm just putting here a very quick summary timeline that highlights the various steps that we've gone through in Italy in order to arrive at the current state of the art, and also somehow pins out the events in time that have seen the superposition between the effort in Italy and the efforts that have been undertaken at the European and also at the more in general international level. So let's try and focus just a bit on the three main goals of the tool in question. The first one was really simplifying the use of cybersecurity frameworks, and we try and do that, and I will try and also expand a bit on this at the end of my presentation. We wanted to allow for more automation when you create a project that is all about assessing the level of resilience of an infrastructure that you are evaluating in some way. We wanted to be sure that the professionals involved in such an activity might have access to all of the regulatory information that is at hand, that, as I was saying in the beginning, is really chaotic now because there are huge quantities of data and heterogeneous sources of information. And obviously we wanted also to give access to a sort of tailored, personalized portfolio of projects. And this will be something I will again expand a bit into. Just to give you an idea of the structure of the interface that we provide to the end users, you typically have all of the functions related to cybersecurity requirements. We identify the categories. We also list the potential subcategories that are associated with each and every category. And we also put a dedicated column that is highlighted here with the red arrow that just puts all of the informative references that are useful in order to better understand the core meaning of the function at hand. The second goal was all about clearly identifying the difference between OT and IT security requirements. I think that here you are all security experts, so I won't dig too much into the details. But obviously, when it comes to identifying requirements, it's not just a matter of stating, I have confidentiality, integrity, and availability. It's also a matter of properly prioritizing them. So as you might know, for OT, for example, availability is first-class citizen. And in IT, typically, we start by giving a bit higher priority, perhaps to confidentiality. So there is a need for somehow cross-mapping such requirements when you are tailoring your study to a specific operational environment. And basically, here, there is some documentation that comes at hand and that is very useful, and I'm referring to the NIST SP800A2 revision document that provides a very detailed guide to industrial control system security and basically provides a sort of tailoring approach that can be leveraged in order to properly fine-tune the project you're working on, depending on specific scenario you want to apply the project to. So I will skip the details here, but you will find the details in the paper. Basically, we use bolded representations, underlined representation, and stroked out representations in order to properly highlight the mapping in question. The third goal, as I was saying, this is third just in terms of sequencing, but not just in terms of priority. And it is about training and also self-training. Obviously, we confronted ourselves with existing state-of-the-art frameworks that are all about cybersecurity assessment. I'm referring to things coming basically from the NIST Institute and also the FNCS framework. And in our case, we typically comply to most of the information sources that such tools are providing, but we also have a number of other sources of information that are listed here. As you can see, there are most of the regulatory documentations that you can find when it comes to assessing resilience of an infrastructure or at large the cybersecurity level of an infrastructure. Okay, we also have a dedicated educational section that contains basically 8 vertical drill down let's say analysis of the things that you might be interested in too when it comes to either self-learning or learning when you are doing some let's say educational activity. Now, just to steal 3 more minutes from your time, I just put here a very quick demo. I asked Jo to work on this, and she basically did a very nice screen recording, just to give you a flavor of how, the whole thing works. You can see this is the main user interface. This is a web application. You have 3 main services that are provided. As I was telling in the beginning, you have access to the 3 main sources of information that are currently available. This is an example of the contextualization related to GDPR. You have other contextualizations. You can typically browse through them. As you can see here, you can have a look at each and every normative reference. You can have access to the details, which are typically abstracted from the original sources. I have to say that Jo did a huge work in extracting all of the information and properly structuring it in form of an ER database that is the back end of the system. You have access to the, I would say, most up-to-date information that is currently available. We are also, as I will show in a second, keeping an eye on the updates to the standards, because as you know, this is something that is very dynamic. Things are changing. So typically, for example, if you take the NIST SP853 revision, there's been in fall 2020 an update to such documentation that has quite a significant impact on the document itself. So we are giving our users the chance to have access to the updates, filter through them, and just verify and double check whether or not the information that is in the current standard has been modified. This is the part related to browsing through the chaos of information that I was mentioning in the beginning. Now we can just have a very quick look at the other two functions, which are basically very strictly related, I would say. As you can see, if you browse through the services menu, you can there find one specific part that is dedicated to the design of a new project. So basically you can create in the blink of an eye, or I would rather say in the click of a mouse, you can create your own project. Here with a lot of creativity, we are creating an ITASEC21 demo project. When you select your project, you can basically browse through all the normative references. You can select the items you are most interested in too. And once you are done, you can somehow start saving your project. Obviously, you might change your mind, and in such a case, you can go back to the editing session. You can select other items and make the proper modifications. Once you are done, you can commit your changes. When you commit your changes, you basically have your project be added to your personal portfolio. And this is the very last feature that I will discuss. As you can see, when you have a project, basically you have all of the information that is extracted from the original sources. You can have access to all of the details, and you can also write down your personal notes. For example, here, just to give you a flavor, I'm copy-pasting information from the original informative reference to my personalized project. I can have it inserted here. And when I'm done, I can just commit all of the modifications. And once again, if I go back to my portfolio, I will see that my project has been saved and it is part now of my personalized portfolio. So that's basically it. It would have been nice to have a live demo of the project, but indeed this was really just to give you a flavor. Let me just add that we are using such a tool in order to really give people a facilitated access to the information that you typically have to make available when you teach something about regulatory approaches to security assessment. So this is very useful for us, and I think that this might be leveraged by other researchers as well. So I have to say that this basically concludes my presentation. This is just a summary of the main features of the tool itself. And again, I'm just stressing the point that the overall idea, the core of the project, is all about raising awareness about cybersecurity. So I'm done with this. If you have any questions, I will be glad to take them. Otherwise, Mario, I can leave the floor back to you. Thanks a lot.
Thank you for the presentation. Let's see if we have any question from the audience. I just recall to you that we have a question and answer feature for WebEx, where you can type your questions so that we see it. I have a question in the meanwhile for you. So, which is the target of your system? It is like other researcher to get the documentation. You're thinking to targeting the OT people that is doing like the operation, so that they actually know what they need to implement.
Mario, let me say this is a great question indeed. the main target is small and medium enterprises, if we talk in terms of business. So there are enterprises who find themselves in the real need of having people become acquainted with such concepts. And this is a matter of compliance also to, standards and regulations. This is one of the main objectives. But really, the objective that I'm personally most interested in too is really training and education. I can tell you that, for example, Joe Mùrino has already used such a tool for a series of lectures that she has given to the Resia people. People who work in the cybersecurity field and who are part of the defense of our country. And this has been very successful. The difficult part of getting acquainted with regulations is that you really find yourself lost in a chaos of information. It's really too much. And you really need someone or some automated tool, in our case, that can help you figure out what are the main items you are really interested in being compliant with. So this is part of it. But I think that there are a number of different ways you can really leverage this framework, and we still have to explore some of them.
We have a question from the audience. They're asking if the tool is freely available online. It's public.
Okay, it's not yet freely available online. This is currently a bit more than a prototype, but it's not market ready, I would say. And I believe this might be released at least in part as an open source project. But I still have to figure out together with my colleagues what is going to be the best approach with respect to this. But really feel free to get in touch with us if you want to have more information about this, and we are definitely willing to share our work with the community.
Okay, that's great. So thank you, Professor Romano, for your presentation.
Thank you.
I would say we will move on to the next speaker. Next speaker is Ivan Vaccari from the CNR. Ivan, can you hear us?
Yes, can you hear me?
Yes.
Okay.
So we are waiting for your slides, and then we can start.
Yes. Can you see the screen?
Yes. Okay.
Okay.
So Ivan, the floor is yours.
Thank you. So good afternoon. I am Ivan Vaccari from I'm a research fellow at Consiglio Nazionale Ricerche in the Network Security Group. And today I'm going to present our work focused on the execution of cyber attacks by using IoT devices as attack vector. In particular, we investigate the Esp8266 module. So a brief introduction about IoT. IoT is a consolidated technology where simple objects gain ability to store, process, and exchange information among themselves or with external entities. From a report of Statista, today there are more or less 35 billion of IoT devices connecting the world, and the number will increase in the next years. So why it's important, the security about Internet of Things? It is important since IoT devices are adopted in critical environments, structures, for example, hospital, power plants, banks, bridge, roads, and so on. And also these devices are adopted to monitor and control personal health information. In this network, sensitive information are exchanged between devices, and also IoT devices have limited computing power. For this reason, sometimes security aspects are not considered. Finally, IoT devices may be exposed on the public internet, and the devices could be possible targets from hackers. So cybersecurity aspects about Internet of Things is a critical and trending topic. In the last years, some vulnerabilities on IoT devices have been exploited to execute cyber attacks or to retrieve sensitive information. One interesting attack on IoT is related to the cardiac devices from St. Jude. In this attack, malicious users could remotely access the devices and retrieve patients' information, and also could control the device by changing its functionalities. So the aim of this attack is to exploit a vulnerability inside the device in order to retrieve sensitive information. Then another interesting attack is Mirai. Mirai is the most famous attack on IoT. The aim here is to exploit IoT devices to execute a cyber attack, in particular to execute a flood attack against the DNS service. During the attack, some famous applications were not available, for example, Amazon, GitHub, Netflix, and so on. Here, the aim is to exploit IoT devices to execute a cyber attack. So these are some examples of cyber attacks on IoT by exploiting vulnerabilities or by using IoT devices as attack vector. Due to the criticality of this topic, we started to investigate the security about the Internet of Things. So we defined a research multi-step approach composed by 3 different phases. In the first phase, the aim is to perform a deep study of communication protocols and devices in order to identify possible vulnerabilities. In the second phase, the aim is to develop innovative cyber attacks in order to exploit the identified vulnerability or to execute cyber attacks by using IT devices as attack vector. In particular, we are working on network and application layer threats. And finally, the last point is related to the development of protection system based on innovative algorithms or machine learning techniques. We applied this approach on 2 different contexts. The first one is related to low-layer protocols such as Zigbee and Wi-Fi. The second one is related to application protocols such as MQTT or CoAP. So in this work, we will focus on the Wi-Fi communication protocol since it is one of the most adopted communication protocol in the world, and it is also widely used in the IoT context. Then we implemented a Wi-Fi based IoT network composed by devices of different nature. A first part of the network is called do-it-yourself. In this network, we implemented all the sensor at the software and hardware level by combining microcontrollers with other sensors, for example, temperature, humidity, CO2, and so on. The second part is composed of commercial devices such as smart camera or motion sensor. Finally, the last part is composed of smart speaker. But in this work, we focus only on the do-it-yourself part. In particular, we focus on the Esp8266 module. So the Esp module is a microcontroller with low computational capabilities and low memory for instructions and data. This module is interesting since it is able to communicate over the Wi-Fi BGM protocol by using different authentication approaches, and also it is compatible with external sensor to implement custom application by exploiting the GPO pin. Also, this module is very cheap since it costs more or less 5-10 euros. The module is programmable through different programming languages, for example, Arduino, C, Python, or other SDK. Also, it is able to communicate over different Wi-Fi wireless communication protocol, for example, Wi-Fi, MQTT, CoAP, and so on. And as mentioned, it is compatible with different sensors. So the challenge of this work is to use the Esp module to execute cyber attacks. While the typical use of these devices is to retrieve information from sensors, we decided to validate if the Esp module could perform cyber attacks, despite its computational constraints. So initially, we implemented a captive portal attack that requires low computational capacity, and then we focus on an innovative denial of service attack that instead requires greater computational resources, since the module should manage hundreds of connections at the same time. So the first attack implemented is the captive portal, which is a social engineering attack. In this attack, the aim is to retrieve sensitive information about victims. In particular, the ESP module creates a free fake Wi-Fi network to steal Facebook credential of the victims and store the credential inside its memory. So the workflow of the attack is reported in this image. Initially, the ESP module creates the fake Wi-Fi network and instantiates the network. Then, when a victim requests the network access, the ESP module simulates a federated login through Facebook to authenticate the victim on the network. When the victim inserts the credential, the ESP module stores the credential on its storage and closes the connections without allowing the victim to browse over the internet. So this behavior is similar to free Wi-Fi network found, for example, in cities. We didn't test this attack in a public place since the information retrieved by the attack are extremely sensitive. So we carried out some tests in our laboratory with fake credentials. In addition, the module during the attack was powered by 2 AA batteries, and the module was able to keep the free Wi-Fi network alive for more or less 2 weeks. So the attack is successful, and then we moved to the denial of service attack. In particular, we implemented a slow denial of service attack, which is an innovative attack that requires low resources and low computational power to be executed compared with classic denial of service attack. So in this attack, the aim is to instantiate all the available connections on an Apache server, which is a well-known open source web server adopted to develop a web application. The Apache server is able to manage 150 connections, and the aim is to instantiate all the available connection and to maintain this connection alive during the attack in order to avoid legitimate connection on the server. So the obtained results are reported in this figure. So as you can see, after a few seconds from the start of the attack, the ESP module is able to instantiate all the viable connection on the server and to reach the DOS status. In this status, legitimate requests are discarded by the server. After some time, there is a reduction of the connections instantiated by the module, probably due to the limited computational capabilities of the ESP module. Then, after this point, the ESP module reinstantiates all the viable connections and reaches the DOS state again. As reported in the image, the DOS status is not maintained for all the attack time, but it is the scope of future work to optimize the attack to keep the DOS status alive for as long as possible. So also the slow denial of service attack is successful. In conclusion, the ESP module is able to execute both the proposed cyber attacks. The first future work will be the optimization of the cyber attacks developed in this work. In particular, in the case of the slow denial of service attack, we will work to extend the attack time by keeping the connection instantiated by the ESP module alive for a longer time. Then we will perform an evaluation of the power consumption required to execute these attacks. Then we will work in order to implement other possible cyber attacks by using the ESP module as attack vector against Wi-Fi or other IoT communication protocols such as MQTT or COAP. And finally, we will perform a security evaluation of the ESP module in order to identify possible vulnerabilities or issues on the module. That's all, and thanks for your attention.
Thank you for your presentation. We have a question from from the audience. I'm gonna read it for you. How did you deal with? How did you deal with HSTS, HTTP strict transport security, when intercepting credentials sent through the Facebook fake Facebook page?
Sorry,
so the question is,
okay.
Yeah, sorry. So the question is, how you dealt with the HTTP strict transport security to intercept the credential for the Facebook fake page?
In the captive portal, the behavior of the attack is quite simple. So the module creates a simple free fake Wi-Fi. All the communication are in plain text. So we proposed a very first approach on this attack. During the development of the attack, we didn't manage this part until now, but we will work on it.
Okay, I don't know if this answered the question. I think yes. I will say we move to the next speaker. Okay, thank you, Ivan, for your presentation. So the next speaker is Vita Barletta from University of Bari. Vita, can you hear us?
Yes.
Okay.
I share my screen.
Okay. Let's see. Okay, we see your screen right now. You can start as soon as you're ready.
Okay, thank you. PhD in Computer Science, and today I present the work on an overview on security technological level in the Italian smart city. The other authors of this work are Paolo Buono, Danilo Caivano, Giovanni Di Mauro, and Antonio Pontrelli. We start our work on the concept of smart city that is a multidimensional entity based on information and communication technology and the intelligent use of urban infrastructure. Starting to this concept, the problem in this context is the security management of technologies and the service, because the increase of the device connected on internet increase the cyber attack and the vulnerability in the product delivery and the service in smart city. So our goal is to analyze the distribution of vulnerable device in smart city in order to understand the security level of the cities. And in order to achieve this goal, we identify in literature the key element for developing and managing smart city. We identify this element and develop an integrated model in order to analyze the security on the smart city. We identify in this model two dimensions: horizontal dimension that represent the technological layer, and we identify 4 layers in this dimension: network and infrastructure, sensor, service delivery platform, and application service. Instead, vertical dimension include the application domain in smart city. So starting with this model, we carried out an analysis of internet connected device available in Italian smart city. And for this analysis, we use a showdown a search engine for internet connected device that scan the internet IP. And in the first step, we analyze the distribution of IoT device in all Italian territories, and we select in this research hour the cities with the highest number of IoT device. So the result of this city that include the maximum IoT device are Rome, Milan, Turin, Bari, and Naples. And we analyze more than 300,000 exposed IoT device in this smart city. So for each device that we selected, we collected the following information: the city, TCP port, and IoT protocol for each device. And the results that we obtain are the following. For distribution of webcam, we see that Rome has the most IP camera. Most of them use the 554 port that is considered less secure. And the second in this chart, and the second smart city that include the highest device on this port are Milan. So regarding the amount of device using VoIP on 5060 port, Rome has the most device connected to internet, but Turin in this case is the second smart city. And this show a general tendency in this case to use more voice service in Turin than in Milan. And regarding to the previous chart, less webcam in this case. According to the IP port, in this chart, we see the use of IP port for 3 different services: file transfer protocol, secure shell protocol, and remote desktop protocol. In this case, we see that secure shell protocol in Milan is much more than is much more used than file transfer protocol. This show more usage of, in this case, secure shell connection that are typical made using terminal. Moreover, in Rome, in this chapter, the number of file transfer protocol is almost the sum of secure shell connection. Also, we analyze the TCP port in industrial context. In this case, the port 2000 contain the maximum number of devices that we analyze in our work, and such ports are more used on SCADA system, which are intended for monitoring and controlling distributed industrial system. This is very visible in Milan city that has the highest number of TCP port, and it is in line with the soul of the city that is projected to innovation and progress. Turin in this charter is the second city in the use of industrial device, and which is not surprising considering the industrial history of the city. what is the surprising is the ROM that use most device on port 2000 and so on the SCADA system. So in our research, we analyze the internet device device on Shodan, and Shodan, thanks to Shodan, we obtain interesting data on this device, and interesting data information with the possible of an attacker to exploit this vulnerability and perform the attack on this device. We starting from the integrating model that we develop in order to analyze the Italian smart city, and in this research work we focus on horizontal dimension, and especially in the network, in the layer of network infrastructure, sensor, service delivery platform, and application service. The results show that the most of devices are in layer 1 in network and infrastructure, so in industrial device, and in layer 4 in application and service, because we analyze most of these devices in the category of IP camera. In the next work, in the future work, we analyze all city in the all Italian smart city, and we plan to focus our research on in order to create a specific visualization of data in order to obtain an overview on this on the security on Italian smart city. Thank you for your attention.
Thank you, Rita, for the presentation. So let's see if we have any question from the audience. Meanwhile, I have a question for you. My question is about the data that you collect from Shodan. Did you especially did you actually try to connect to this IPM port and see the message there, or the data is just collected from Shodan?
Allora, so we use the API of Shodan in order to obtain the list of the webcam, the IP of device and protocol, in order to analyze on the different level on the smart city the device, and in order to obtain from the data collected from Shodan the possible vulnerability that an attacker exploit in order to perform the attack on this device. And so in this case, this information that we obtain, it is more important because on the smart city there is different smart project that use this device, and from each project that focus in more case on the single domain or on the single layer, that is very important to provide a guideline in order to manage in a secure manner this device on the smart city.
Okay, thank you. So I don't see any question from the audience. I think we can move to the next speaker. Thank you again, Rita, for your presentation.
Thank you.
Next speaker, meanwhile, is Fatima Nazari. I hope I didn't butcher your name. And I'm sorry.
Yes,
maybe.
yes.
Okay. So we can hear you, Fatima. Try to share your presentation. Okay, we see your screen.
Okay. And sorry, I can.
Okay.
Present.
So as soon as you're ready, I think we can actually start.
Yes. Hello, everybody. My name is Fatima Nazari, a second-year PhD student from Department of Electrical Engineering and Information at Polytechnic Dubai. Okay, I'm going to present to you our research work, which is named Revisiting Security Threat on Smart Grids, Accurate and Interpretable Fault Location Prediction and Type Classification, under supervision of Prof. Ardita and Prof. Dishasha. Okay, what is a smart grid? A smart grid is a modern version of a traditional grid, electrical grid. The goal of this modernization is to create two-way communication between power utilities and consumers, where both information and electricity can be exchanged for enhancing efficiency, stability, and safety. However, power distribution systems are susceptible to a variety of electrical abnormalities and occasional failures as a result of, for instance, adverse weather condition, equipment aging and degradation, and security attacks, among others. Okay. There are certain security objectives that have to be satisfied to ensure security in a smart grid. They include confidentiality, integrity, and availability, or the CIA triad. In addition to the security objectives, there are certain security requirements that need to be fulfilled to ensure security in smart grid applications. Okay, they include authentication, accountability, privacy, dependability, survivability, and safety criticality. Okay. In this work, we focus on the dimensions, dependability, survivability, and accountability, and study them in a real-life simulation of the electrical grid and fault scenario. Okay, a smart grid can be reliable by considering self-healing features. Fault detection, classification, location detection are the main features that can make the smart electrical grid reliable to recover the interruption of electricity in the electrical grid automatically. Okay, so the research goal is to fulfill 3 security requirements, which I said in the previous slide. Okay, what is dependability? Sorry, I just jumped to the next slide. Sorry about that. What is dependability? Dependability is the capacity of the system to deliver its services in time and accurately. And that services are delivered even during fault periods. A requirement for ensuring dependability includes fault detection, fault forecasting, in which fault type classification refers to this part. Okay, what is survivability? Survivability aims to deliver services both in existence of malicious activities and external faults. Fault location and security policies are among prominent measures for survivability. And finally, what is accountability? Accountability allows understanding who is responsible for a problem in times, which is achieved by providing more transparent evidence about the grid functioning. So we want to know why machine learning system made certain fault location prediction or type classification decision. Okay, the goal of the proposed method is multifold. First, information processing and prediction. We considered 5 different supervised classifiers for fault location prediction and fault type classification. And second, interpretability to visualize the impact of features and their relationship on the classification outcome, and large-scale dataset. We use a large-scale dataset containing 1,848 measurements. Okay, the pipeline of proposed fault analysis is as follows. First, simulation of IEEE 13 node test feeder. Second, fault injection in 4 critical zones and measurement of 3-phase voltage signals. Third, extracting time transform domain features and transfer domain features, which are discrete Fourier transform and discrete wavelet transform. Multi-class single label classification, and finally interpretability by visualization of feature interaction importance. Okay. As you can see here, we use the IEEE 13 node test feeder, which is a distribution network operating at 4.16 kilovolt. It consists of a set of characteristics that are in common with actual networks, such as unbalanced loads, voltage regulator, and so on. And also, it consists of 4 critical zones, which are shown by red circles where different faults were injected in this picture. Okay. Data collection is done as an input for classifier. A module named 3-phase fault has been applied on 4 critical zones, which are highlighted in figure previous slide. In particular, these faults include line to ground, line to line, line to ground, and 3-phase fault. And also, to augment the training data set with further data, we consider 22 different fault resistance. Because of that, fault simulation is done 22 times for each fault types. Okay, features are extracted from 3 different domains and from the 3-phase voltage signals. In time domain, 6 features extracted. These features are computed from the distribution of signal in faulty period and non-faulty period. They include the first 4 moments: mean, standard deviation, skewness, kurtosis, together with max and energy of the signal. After calculation, 2 respective values are divided to provide a relative feature of faulty period over non-faulty period. After that, these 6 features are also extracted in the transfer domain, which I mean discrete Fourier transform and wavelet transform. Just in the wavelet domain, we have multi-resolution analysis. So for wavelet, we use the 6 coefficient. So 6 multiply 6 aggregation operation, we have 36 features just for discrete wavelet domain. Okay. Fault location prediction and fault type classification were carried out by using 5 different supervised classifier, decision tree, support vector machine, k-nearest neighbor, ensemble methods, which we use backtree and subspace k-nearest. And for interpretability experiment, we use a decision model informed approach involving visualizing the impact of pair of features that have the highest impact on the classification task. Okay, this slide shows the result of classification for fault location prediction and fault type classification with different domains and combination of these domains, I mean time, frequency, which is related to discrete Fourier transform, and wavelet. According to this table, in highest accuracy for fault location prediction is 100%, which is achieved by combination of all domains and ensemble subspace k-nearest classifier. And for fault type classification is 95.4%, which is achieved by combination of all domains again and with support vector machine classifier. About the quality of domains in classification, we can understand that the combination of domains and after that wavelet alone had a high impact on classification. Okay, the visualization of feature importance analysis is shown in this heat map. Here we illustrated the result of fault location prediction with decision tree classifier for interpretability analysis. As you can see, the heat map shows the impact of both feature class, which I mean domains. We had 3 domains: time, discrete wavelet transform, and discrete Fourier transform, with 48 features and their pairwise relationship on fault location prediction. The yellow region shows the features that are mutually informative, and dark blue region shows features that are not mutually informative. Okay, it can be noted that the most orange and yellow regions, which correspond to highly accurate classification outcome, are related to discrete wavelet transform. In other words, the discrete wavelet transform feature class or domain contains more discriminative information in comparison with other, which I mean time and frequency domain, which are mostly in blue colored regions. So finally, we can say that by looking at the result in discrete wavelet transfer part, we can note that the majority of yellow regions belong to kurtosis, skewness, and mean, together with discrete wavelet transform. Why we did it? Because this information could eventually be used by system designer to know which features to focus on for extraction phase from the smart grid signals, and by the system human operator to understand the root of a specific fault in the system. Okay. In conclusion, we had addressed the security threat by considering 3 requirements for it: dependability, survivability, and accountability. We did data collection as a classification input for fault location prediction and type classification by simulation of IEEE 13 distribution network and fault injection. And then feature extraction by considering 3 feature class, which I mean domain. And finally, we refer to accountability by interpretability. Okay, thank you for your attention, and please feel free if you have any question.
Thank you, Fatima, for your presentation. As before, if you have any question from the answer, please you can type it on our question and answer form. In the meanwhile, I have a question for you regarding mostly the simulator that you used. So my question is, because it's a simulator,
Yes.
how good is with respect of reality? And do you think the fact that you use a simulator actually is helping your system to learn better than what you could learn in a real system where there is no simulation? You may have extra noise on the measurement.
For sure, you're right. Because because we didn't have real data, and we just could do this by simulation. But simulation, as I said in the in one of my slides, that this distribution network, for instance, which I use, IEEE 13 node test feeder, is work like a real one. So we can do this, we can simulate it, and we can say that, yes, it can be, it cannot be in a real situation, but it can simulate that situation. Unfortunately, we didn't have real data from company, and also we just could do it.
Thank you. So do you think that in a real scenario you will need like more data to have the same performance, or do you think it's I mean, more or less the same?
It depends. It depends, because as you did, we did anomaly detection, fault detection here. Maybe in a real scenario, we can have many cybersecurity attacks also here. So in the near future, we will work in a system who could not only detect anomalies, fault, but also could detect some real attacks by applying adversarial machine learning. I think in this situation could simulate it in a real situation.
Okay, thank you very much for your answer.
You're welcome.
So I think we can move to next speaker. Thank you again for your presentation. For today, our last speaker on the list is Eduardo De Paulo from University Sapienza in Rome. Eduardo, can you hear us?
Yes, I'm sharing the screen.
Okay, thank you.
Okay,
okay, so here we are. Eduardo, you can start as soon as you're ready.
yes. So I am Eduardo De Paulo, and I am a computer science student at La Sapienza. And with Enrico Bassetti and Angelo Spognardi, we did security assessment of common open source Mqtt brokers and clients. So I started from an introduction. So in the recent years, the IoT field has grown very rapidly, and several new protocols were implemented. And one of them is Mqtt, that is one of the most used in this field. And we can see in this slide, for example, the number of devices using Mqtt that are indexed that was indexed on Shodan in the 2018 and in 2021, and we saw that there is a difference, big difference, and this represents the growth of the IoT field. The protocol itself, it's very simple. It follows a publish subscribe pattern, and it offers to the user also 3 different levels of quality of service: level 0, level 1, and level 2. And in an architecture that uses Mqtt, the clients will not communicate directly each other, and they can communicate through the topics that are simply string that are just a string in the subscription or public or publish packet. And to communicate in the architecture, we have a main component that is the Mqtt Broker. And to the Mqtt Broker, we can connect with our devices, smart devices, for example, the smart home devices, sensors, or also light bulbs, for example. And these devices will publish some information like the temperature or humidity in a room over a topic that is like a communication channel. And they will publish some information, and we can receive this information by subscribing, for example, with our laptop to the specific topic that is in the published packet, or also from some servers or a PC desktop, and also from our smartphone, so we can remotely manage all the devices through an Mqtt architecture. In our case, we studied in particular 5 different broker libraries that are pretty used in the Mqtt community, that are Mosquito, EMQX, HiveMQ, Mqtt, and EDES. And 3 different client libraries that are PAO Mqtt, Mqtt.js, and Mqtt tools. And we performed several experiments among those libraries, and we performed a dynamic analysis using a fuzzing methodology. We wrote a fuzzer in Python, and in particular, we focused on many topics. For example, we did experiments about the quality of service flows, and one experiment is as we can see in this table, the publish quality of service 2 and 1, where the client subscribes to a topic and then publish two packets with the same packet ID, but with and then it sends 2 packets, one as the quality of service of level 2, and the second one as the quality of service of level 1. And for example, in this case, we saw that one broker, Mosquito in particular, drops the second packet. So the clients that are subscribed to the topic specified in the published packet will receive only the first packet sent, that is the one with the quality of service of level 2. Then we tried also a similar experiment that consists to send a first packet with a quality of service of level 2 and the second with a quality of service of level 0. And then we tried also to send the same packet with a quality of service of level 2. And also in this case, even in this case, Mosquito drops the second packet, for example. And also, we tried a long topic experiment to see how the brokers behave on a long topic. For example, in EMQX, we have a limit of 4,096 characters for the topic's length. And this fact do not respect the standard that is defined for Mqtt. And we performed also other experiments. For example, we tried to send the malformed packets to see if the brokers accept them or not. For example, we tried to send a connect packet with an invalid protocols version, and we saw that all the brokers reject the connection, the client connection, and reasoning it. And also we tried, for example, to send a packet, a connect packet with a keep alive field encoded as a string, or we tried some subscription or publication to an invalid wildcard, and also some packets flood experiment. And we saw that in this case, for example, the brokers all the brokers behave well. In fact, they handle well all the packets that was incoming, and there was very much. And about the results that we get about the broker libraries, we saw that all the brokers we found some anomalies in all the brokers about the handling of the quality of service experiments. And in EMQX, IVMQ, and Mqtt, also about the experiments that concern the longer topics. And in particular in Mqtt and in Edes Broker, we registered also a possible denial of service on the broker. In Edes, for example, the denial of service happens when we send a packet with a very long topic, About the client libraries, we registered some hangs about the handling subscription to an invalid wildcard in the case of PowerMQTT and Mqtt tools. And in Mqtt.js, we registered a crash of the client when we try to send a packet with an invalid quality of service level. In Mqtt tools, there is also an infinite connection loop when we try to connect with a client ID that contains non-UTF-8 characters in the packet value, in the field value of the client ID. After this phase of testing on the libraries, we tried also the same experiments on a physical device, that is the one shown in this slide. That is a simple light bulb that supports the MQTT protocol. And we saw that all the results that of the previous experiments were also confirmed in this case. For example, when I was saying Mosquito that drops the second packet, we try to send a turn-on packet for the light bulb and a turn-off packet, and we saw that in Mosquito the light bulb only turned on, and in all other cases the light bulb turned on and then turned off, as we can expect. We saw also that this type of devices do not have an anti-flood mechanism regarding the packets that it receives. So it is possible to send, for example, many turn-on packet and turn-off packet in a very small amount of time. And so it is possible to overload the electronic components that are inside the device to make it useless. So about future work, we can repeat the experiments also on the latest version of the protocol of the MQTT, that is the 5th, and see if there are differences between the brokers' behaviors and also the client libraries' behaviors and the physical device. We performed the experiments on the 3rd version of MQTT because most of the devices are using actually the 3rd version and not the latest. Also, we are also investigating on possible vulnerable applications that exploiting one or more of the vulnerabilities that are reported in the paper to see to show also a possible attack scenario in a real world application. So that's all, and thank you for your attention.
Thank you, Eduardo, for your presentation. Do we have any question from the audience? I'll start with a question. So a few years ago, in 2018, at Black at Europe, some people actually presented some vulnerability on MQTT, and one of them was on the quality of service. and in particular was like if the quality of servers is equal to 2, you could exploit the broker to send to flood the client because the messages were always sent. And turned out that the problem was not in the implementation, but was actually in the standard, because the standard actually allowed that. It was a feature of the standard. So my question for you is, the weirdness that you find in the quality of service in the Mqtt in the protocol, are those coherent with the standard, or they are like divergence of the standard and only vulnerability in the clients that you saw?
Well, we saw that, for example, in some experiments, the flow of the brokers about the standard was not respected at all. So we receive, for example, before pubcomp message before the publication, and not the reverse. And so I think that there are the libraries that are not implementing correctly at all the standard that are defined for the MQTT protocol.
The thing you found, they are like stuff that is not coherent with the standard, right?
Yes.
Okay. 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 But is your model like able also to account for the divergence of the standard, in the sense, if the standard has a problem, can you update your system so that you will avoid one of the rules that is causing the problem?
I think, well, I don't know. I mean,
Okay, no problem. I think we can chat about this
okay,
another time. Okay, so thank you, Eduardo, for your nice presentation. This was last presentation for the session. I want to thank all the speakers for their work that they showed us today, and also all the attendees for their time. I hope it was interesting. I think it was. So thank you all for being here today. And that's all for the session.
Thank you, Mario. See you all. Bye.
Thank you.